Hello and welcome to Hafee Sleep, a place where curious minds come to relax and explore the universe's deepest secrets. Tonight we're embarking on an incredible journey, a story of genius, surprise, and breathtaking discovery. We're unraveling the history of the atom and answering a fascinating question. How and when was every single subatomic particle discovered? From the first glimpse of the electron to the hunt for the Higgs boson, we're covering it all in a cozy, easy-to-understand way. So get comfortable, relax those eyelids, and let your imagination drift down to the quantum world. And if your mind is feeling wonderfully expanded tonight, why not let us know? Hit that subscribe button and ring the bell so you never miss our next journey into the unknown. I'd also love to know, where in the world are you watching from and what time is it there? Drop a comment down below and share this moment of discovery with our community of sleepy time scientists. All right, let's begin. This is the story of how we peered into the heart of the atom itself and discovered a whole zoo of particles, a secret society humming with invisible energy. This is the story of how and when we discovered each subatomic particle. So, get comfortable. We're going to rewind the clock back to a time when the atom was still just a philosophical idea, a ghost in the scientific machine, and we'll walk, step by step, through the moments of dazzling brilliance that revealed the universe's deepest secrets. Our story doesn't start with a bang, but with a quiet, curious glow in a dark laboratory. It's the end of the 19th century. The world is changing fast with steam engines and industry, but in the quiet, hallowed halls of physics laboratories, a different kind of revolution is brewing. It's a revolution of thought. For the longest time, scientists had been comfortably settled with the idea of the atom. It was a neat and tidy concept, this notion of a tiny, solid, indivisible sphere that was the fundamental building block of everything. Iron, oxygen, water, you name it. It was a beautiful and simple idea, and it seemed to explain so much about chemistry and matter. But then, along came these fascinating cathode ray tubes. Now to us today, a cathode ray tube might sound like some exotic piece of equipment, but if you're of a certain age, you've actually had one in your house. The old, bulky, pre-flat screen television sets, those were cathode ray tubes. The big, heavy box part was essentially a sophisticated version of the very thing these Victorian scientists were so entranced by. So it's a glass tube, sealed up tight, with most of the air pumped out, creating a partial vacuum. At one end is a negative electrode, called the cathode. At the other end is a positive electrode, the anode. And when you crank up the electricity, applying a seriously high voltage across these two electrodes, something happens in that near-empty space. A ray, a beam, a mysterious something leaps from the cathode and shoots in a straight line over to the anode. But because the anode often has a hole in it, this beam shoots right past it and slams into the glass wall at the far end of the tube. And when it does, it makes that spot glow with an eerie greenish light, a phosphorescent glow. This was the puzzle. This was the mystery that had the great scientific minds of Europe arguing. What on earth was this cathode ray? You could see its effects. It cast sharp shadows. If you put a little Maltese cross, a little metal shape, in its path, you'd see a perfectly defined shadow of that cross on the glowing end of the tube. That suggested it was traveling in straight lines, like a beam of particles. But then, you could also bend it. If you brought a magnet near the tube, the whole beam would curve and the glowing spot would move. This also suggested it was made of particles, because a magnetic field can deflect moving charged particles. But some scientists, particularly the Germans, were convinced it was some new kind of wave, a weird ethereal wave in the ether, because waves were all the rage in physics at the time. What with the brilliant work on light waves? The stage was set. The mystery was begging to be solved. And into this scene walks a quiet, unassuming, mustachioed English physicist named Joseph John Thomson, or J.J. Thomson, as he's known to history. He was the head of the Cavendish Laboratory at Cambridge University, which was quickly becoming the place to be for cutting-edge physics. Thomson wasn't a brash, loud experimenter. He was a thinker, a tinkerer, a man who loved puzzles. And the cathode ray was the most fascinating puzzle of all. Thomson looked at all the arguing and decided the only way to settle it was not with more talk, but with a beautiful, clever experiment. He needed to ask the ray a direct question and force it to give a direct answer. His genius was in how he designed the questions. He thought, if this is a beam of particles, they must have mass. And if they're being bent by a magnet, they must have an electric charge. Therefore, every single one of these particles, whatever they are, must have a specific relationship between its charge and its mass. This is called the charge-to-mass ratio. It's a crucial fingerprint for a particle. Think of it like this. If you're a detective and you find a single hair at a crime scene, you can't yet say who the person is, but you can learn a lot about them. What color their hair is, how thick it is, etc. The charge-to-mass ratio is like that hair. It's a vital clue to the identity of the mysterious culprit. So, Thomson built a special cathode ray tube. It was a work of scientific art. Inside, he put plates to create an electric field. He could use these to deflect the beam up or down. He also set up electromagnets outside the tube to create a magnetic field, which would deflect the beam in the opposite direction, say, down, if the electric field was pushing it up. His plan was brilliant in its simplicity. He would adjust the strength of the electric and magnetic fields until they perfectly balanced each other out. The electric force pushing the beam up would exactly equal the magnetic force pushing it down. The beam would shoot straight through, unaffected, and hit the center of the tube's end. Why is this so clever? Well, when the two forces are balanced, he knew their strengths were equal, and the equations for the electric force and the magnetic force both contain the charge of the particle. By balancing them, he effectively canceled out the charge from the equation. This left him with a calculation that involved only the strength of the fields, the amount of deflection he'd seen before he started balancing, and the mass of the particle. He could now calculate the mass-to-charge ratio, but he did more. He could then turn off the electric field and just use the magnetic field to bend the beam into a perfect circle. By measuring the radius of that circle and knowing the strength of the magnetic field, he could calculate the charge-to-mass ratio directly. He was cross-examining the evidence, checking his work from two different angles. The results were absolutely mind-blowing. The number he got for the charge-to-mass ratio was enormous, staggeringly huge. To understand why this was such a shock, you have to think about the hydrogen ion. A hydrogen ion is just a hydrogen atom that's lost its electron, so it's essentially a single proton, the lightest positive particle anyone knew about. Scientists had a rough idea of its charge-to-mass ratio. The number Thomson got for his cathode ray particle was over 1,000 times larger than that of the hydrogen ion. There were only two ways this math could work out. Either the charge, E, of the particle was astronomically impossibly large, or its mass, M, was incredibly, almost unbelievably small. Since the first option made no sense, the conclusion was inescapable. These corpuscles, as Thomson cautiously called them, were unimaginably light. They had to be over 1,000 times lighter than a hydrogen atom, the smallest thing anyone had ever conceived of. This was the first, earth-shattering part of the discovery. He had found something smaller than an atom. The atom was not indivisible. It had parts. This was like being convinced that a billiard ball was the most solid, fundamental object in the world, and then someone comes along and shows you it's actually made of even smaller, buzzing little specks. It fundamentally rewrote the rules of the universe. The second part of the discovery was just as important. By seeing which way the beams were deflected by the electric and magnetic fields, Thomson confirmed what some had suspected. These tiny, tiny particles were negatively charged. So, he had discovered a negatively charged particle that was a fundamental constituent of the atom. Now let's pause for a second and think about the sheer courage this took. Thomson wasn't just presenting a new bit of data. He was standing before the entire scientific establishment and telling them that a core belief they had held for a century was wrong. He was proposing a whole new model of reality. He was, in a very real sense, the first person to ever see beyond the atom. He had opened a door to a new world, a subatomic world. He announced his findings in 1897. The reaction was, as you can imagine, a mixture of amazement and skepticism. But the evidence was too strong. The particle was soon given the name we know it by today, the electron. The name had actually been suggested earlier by a scientist named George Johnstone Stoney, but it was Thomson's work that proved its existence and gave it its properties. Thomson's discovery of the electron was like the first crack of light in a completely dark room. It immediately raised 1,000 new questions. Okay, so atoms contain these light negative electrons, but atoms themselves are electrically neutral. So if there's negative stuff inside, there must be an equal amount of positive stuff to cancel it out. What is that positive stuff? Where is it? How is it arranged? If the electron is so small, what constitutes the bulk of the atom's mass? Thomson himself took a stab at this. He proposed the plum pudding model. Imagine a Christmas pudding, a very British analogy. The pudding itself, the soft, cakey part, is a spread-out, diffuse cloud of positive charge that makes up most of the atom's mass. Then, dotted throughout this positive pudding, like plums in the dessert, are the negative electrons. It was a lovely, tasty-sounding model. It explained the atom's neutrality. It was a good first guess, but it was wrong, and proving it wrong would be the job of one of Thomson's own students, a brash, brilliant, and loud New Zealander named Ernest Rutherford. Around 1909, he, along with his assistants Hans Geiger and Ernest Marsden, conducted what is perhaps the most famous experiment in all of physics. They took a thin sheet of gold foil, only a few atoms thick. They then aimed a beam of alpha particles at it. Alpha particles are heavy, positively charged particles emitted by certain radioactive elements, though they didn't know exactly what they were at the time. They were like tiny, subatomic cannonballs. According to the plum pudding model, these cannonballs should zip right through the diffuse cloud of positive pudding, maybe getting deflected by a tiny, almost unmeasurable amount. The team sat in the dark, counting the faint flashes of light made by alpha particles as they hit a screen around the foil. Most of the particles did just that. They sailed straight through. But then, something unbelievable happened. Every now and again, an alpha particle bounced right back. It was as if you fired a massive artillery shell at a tissue paper, and it came flying back at you. Rutherford was utterly astounded. He later said it was almost as incredible as if you had fired a 15-inch shell at a piece of tissue paper, and it came back and hit you. This could only mean one thing. The positive charge in the atom was not smeared out like pudding. It was concentrated in an incredibly tiny, incredibly dense, positively charged core at the center of the atom. In 1911, Rutherford announced his discovery, the atomic nucleus. So here we are. Ernest Rutherford, with his gold foil experiment, has completely turned the world of physics upside down. He's shown us that the atom isn't a solid little billiard ball, and it's not even a soft, squishy plum pudding. Instead, it's mostly empty space, a vast, incredible, breathtaking amount of nothing. And right at the very center of all that emptiness is a phenomenally tiny, incredibly dense, positively charged nugget called the nucleus. And whizzing around this nucleus are the tiny negative electrons that J. Thomson discovered. It's a beautiful picture, isn't it? It makes intuitive sense. It's like a miniature solar system. The sun is the nucleus, and the planets are the electrons orbiting around it. It's neat, it's orderly, and it fits nicely with how we understand gravity working in space. There was just one tiny, enormous, universe-breaking problem with it. According to all the well-established laws of physics that had been worked out by giants like James Clerk Maxwell, this atom couldn't possibly exist. In fact, it should self-destruct in a blink of an eye. Let's break down why, because this is the crucial cliffhanger that sets the stage for our next genius. Think about what an electron is doing as it orbits the nucleus. It's a tiny particle with a negative charge circling a positive center. To constantly change direction and move in a circle, it must be accelerating. Now, here's the key part of the physics that everyone knew. When a charged particle accelerates, it must give off energy. It must radiate that energy away as electromagnetic radiation. In other words, as light. This isn't some weird, obscure rule. It's a fundamental principle. It's how radio towers work. An antenna accelerates electrons up and down, and they radiate away energy as radio waves. So, apply that to our planetary atom. The electron is constantly accelerating as it circles the nucleus. Therefore, it should be constantly losing energy. And if it's losing energy, it can't maintain its orbit. It's like a satellite in a low orbit around Earth. If it slows down, its orbit decays and it falls. The electron would spiral inward, getting closer and closer to the nucleus, radiating away a continuous stream of light as it does so. And the calculations showed this would happen unbelievably fast. The entire atom would collapse in less than 100 trillionth of a second. A nanosecond would be an eternity for this process. But that's not what happens. You are made of atoms. I am made of atoms. This script is made of atoms, and we are not collapsing in a flash of light. Atoms are stable. They last for billions of years. Furthermore, when atoms do give off light, they don't give off a continuous smear of all colors, like a rainbow. They give off very specific, very distinct colors. If you heat up an element like hydrogen, it glows with a very particular pinkish red light, not white light. When you pass that light through a prism, you don't see a full rainbow. You see a series of sharp, bright lines at very specific colors. It's like a barcode for that element. Rutherford's model couldn't explain this either. It predicted a continuous smear of light from the death spiral of the electron, not a neat, organized barcode. This was a monumental crisis in physics. The model that explained the experimental data so perfectly was completely at odds with the fundamental theories that had been proven correct for everything else. It was like having a perfect key that simply would not turn in the lock. The rules of the game, the rules of the big world, the world of planets and balls and waves, were failing miserably when applied to the ultra-small world inside the atom. Clearly, a new set of rules was needed. The universe was telling the physicists, "You think you understand me? You haven't seen anything yet." Enter our hero for this chapter, a young, thoughtful, and deeply philosophical Dane named Niels Bohr. Bohr arrived at Rutherford's lab in Manchester, England in 1912, brimming with ideas. He was captivated by Rutherford's new model of the atom, but he was also acutely aware of its fatal flaw. He couldn't accept that the laws of physics were just wrong. Instead, he proposed a breathtakingly radical idea. What if the laws weren't wrong, but they were incomplete? What if the world of the atom operated under a different set of rules, rules that only became apparent at this tiny, tiny scale? This was the birth of what we now call quantum theory. In 1913, Bohr, with a stroke of sheer brilliance, took Rutherford's solar system model and imposed a set of new rules on it. They were rules that made no sense according to classical physics. They were bizarre, counterintuitive, and seemed almost magical. But they worked. Rule number 1. Electrons cannot orbit the nucleus at just any old distance. They are forbidden from being just anywhere. Instead, there are only certain specific, allowed orbits where an electron is permitted to exist. Think of it not as a planet that can orbit at any distance from the sun, but like a chairlift on a mountainside. The chairs can only be at certain fixed stations. They can't just stop anywhere along the cable. Or imagine a theater with fixed rows of seats. An electron can be in row 1, row 2, or row 3, but it cannot be in the aisle between the rows. These allowed orbits were quantized. This was a new idea, quantization. Things could only exist in specific, discrete levels, not a smooth, continuous range. Bohr calculated where these allowed orbits would be for the simplest atom, hydrogen, and his math was based on a new constant in nature, Planck's constant, which we'll get to in a moment. Rule number 2, and this is the real mind bender. While an electron is in one of these allowed orbits, it does something utterly impossible. It does not radiate energy. It can circle and circle and circle the nucleus forever, perfectly stable, without losing a single jot of energy. It's as if the electron is on a special, protected track where the usual laws of physics are suspended. This rule directly solved the collapse problem. The electron wasn't allowed to spiral inward because it couldn't exist between the allowed orbits. It was either on one track or another, and while on that track, it was safe and stable. But wait, you might say, then how do atoms ever emit light? Why does a hydrogen lamp glow? This brings us to Bohr's third radical rule. Rule number 3. Electrons can jump from one allowed orbit to another, but they can't glide or slide. They make instantaneous teleporting quantum leaps. If an electron jumps from a higher energy outer orbit to a lower energy inner orbit, it can't take that extra energy with it. So it spits out the excess energy in one precise, specific packet of light, one single particle of light, which we call a photon. And the energy of that photon exactly equals the difference in energy between the two orbits. Conversely, if an atom absorbs a photon of light with that exact same energy, it can kick an electron from a lower orbit up to a higher one. This was the masterstroke. This explained the mysterious barcode. Each line in hydrogen's spectrum wasn't just a random color. It was a direct readout of the energy difference between two of these allowed orbits. An electron jumping from orbit 3 to orbit 2 would emit one specific color of red light. Jumping from orbit 4 to orbit 2 would emit a blue-green light. Every jump between specific orbits produced a specific color. Bohr, with his new model, was able to calculate the exact wavelengths of light for these jumps in the hydrogen atom. And when he compared his calculations to the known spectral lines of hydrogen, it was a perfect match. Not a close enough match. A perfect, precise, stunningly accurate match. It was one of the most triumphant moments in the history of science. Where did these strange rules come from? Bohr was building on an idea proposed a few years earlier by the German physicist Max Planck. Planck had been struggling to explain the light emitted by hot objects, like a red-hot piece of iron. He found he could only explain it if he made a crazy assumption, that energy was not released in a smooth, continuous flow, but in little tiny, indivisible packets. He called these packets quanta, from the Latin for how much. It was as if energy came in tiny atoms too. This was the concept of quantization. Planck thought it was just a mathematical trick, but Einstein had taken it seriously, using it to explain the photoelectric effect. Now Bohr was taking this idea of quantization and applying it not just to energy itself, but to the very structure of the atom. Bohr's model was a wild hybrid. It was a mix of the old classical world, planets orbiting a sun, and the new quantum world, fixed orbits, quantum leaps. It was a bit of a fudge, and Bohr knew it. He couldn't explain why the orbits were quantized. He just imposed that they were, and it worked spectacularly well for hydrogen. It was a stepping stone, a crucial bridge from the old physics to the new. It saved the atom from collapse, it explained atomic spectra, and it boldly declared that the subatomic world was a place where the everyday rules of reality did not apply. It was a place of allowed and forbidden zones, of sudden jumps, and of energy delivered in precise little packets. It was strange, it was beautiful, and it was just the beginning. The quantum revolution had begun, and it would soon get even weirder, introducing us to a world of wave-particle duality, uncertainty, and a fundamental fuzziness at the heart of everything. But for now, let's tip our hats to Niels Bohr. He looked at an atom that was impossible, and with a breathtaking leap of imagination, he gave it a set of new rules. He gave the electron a stable home and showed us that sometimes, to find the truth, you have to be willing to believe in the seemingly impossible. The crisis was averted, for now. But Rutherford, our boisterous pioneer from New Zealand, was not a man to rest on his laurels. His discovery of the nucleus had opened up a whole new frontier, and his mind was fixed on that tiny, dense core at the heart of everything. What was it made of? He already knew it was positively charged because it had to balance out the negative charge of the electrons buzzing around it. And he knew it was heavy, containing almost all of the atom's mass. The most obvious idea, the simplest hypothesis, was that the nucleus contained positively charged particles. After all, they had just spent years discovering that negative charge came in neat little particles called electrons. Surely positive charge must come in a particle form too. Rutherford thought so. He even gave this hypothetical positive particle a name drawn from the Greek word protos, meaning first. He called it the proton. It was a great name, suggesting it was the primary, the first building block of all matter. but having a hypothesis and proving it are two very different things. How do you find a single particle inside a nucleus that is 100,000 times smaller than the atom itself? You can't just peek inside. You have to smash it open and see what flies out. And that's exactly what Rutherford decided to do. He became the world's smallest, most precise demolition expert. His tool of choice was, once again, the alpha particle. Remember, these were the heavy, positively charged bullets he had used in his gold foil experiment. They were emitted naturally from radioactive elements like radium. He had a ready supply of these subatomic cannonballs. His target this time wasn't gold foil, but something much lighter, nitrogen gas. He set up a beautiful experiment. He had a small chamber filled with nitrogen gas. On one side, he placed a source of alpha particles so they would shoot into the chamber. On the other side, he had a screen coated with zinc sulfide, a material that would flash with a tiny spark of light when it was struck by a charged particle. It was a dark room job, just like the gold foil experiment, requiring hours of sitting and patiently counting these tiny scintillations of light. He started firing alpha particles into the nitrogen gas. Most of them zipped right through the empty space of the nitrogen atoms, just as you'd expect. But every now and then, something truly extraordinary happened. He saw a flash on the screen that was different. It was brighter, and it happened even when he put barriers in the way that would stop any alpha particle. It was as if his alpha bullet had hit something inside the nitrogen nucleus and knocked out a new, even smaller bullet. He was astounded. He carefully analyzed the tracks of these new particles using a cloud chamber, a device that makes particle tracks visible as tiny condensation trails, like the jet trails of a plane. And he measured how they were deflected by magnetic fields. The results were clear. The new particles had a positive charge, and their mass was exactly what he had predicted for his proton, about 1,800 times the mass of an electron. He had done it. In 1917, in the middle of the First World War, Ernest Rutherford had artificially transmuted an element and discovered the proton. He had taken the nucleus of a nitrogen atom, and by bombarding it with an alpha particle, knocked a proton right out of it. In the process, he had actually changed the nitrogen atom into an oxygen atom. It was alchemy of the most real and scientific kind. He had shattered one nucleus to find a fundamental piece of another. This was a monumental discovery. Now the picture of the atom seemed almost complete. The nucleus was made of protons. The number of protons in the nucleus determined the element's identity and its place on the periodic table. Hydrogen, the lightest element, had 1 proton. Helium had 2. Lithium 3, and so on, all the way up to uranium with 92. The atomic number, which chemists had used to order the elements, was simply the number of protons in the nucleus. And orbiting this positive nucleus were enough negative electrons to exactly balance the charge, making the atom neutral. It was elegant, it was simple, and it explained so much. But, as always in this story, just when everything seems settled, a new problem rears its head. And this one was a real head-scratcher. It had to do with weight. Let's take helium as an example. A helium nucleus has 2 protons, so its charge is +2. But if you weigh it, its mass isn't twice that of a single proton. It's about 4 times heavier. Where was this extra mass coming from? It was like packing 2 bowling balls into a box, and finding the box now weighs as much as 4 bowling balls. It made no sense. Scientists looked at all the elements and saw this pattern everywhere. A carbon atom has 6 protons, but its mass is equivalent to about 12 protons. Oxygen has 8 protons, but a mass of 16. It was as if every nucleus had extra hidden mass inside it. But what could it be? It couldn't be more protons because that would change the positive charge and therefore the identity of the element. A helium nucleus with 4 protons wouldn't be helium anymore. It'd be beryllium. So the extra mass had to be coming from something that had mass, like a proton, but carried no electrical charge, something neutral. The idea of a neutral particle in the nucleus had been floating around for a while. Rutherford himself had mused about it, even playfully dubbing it a neutron as early as 1920. But how do you find something that is, by its very nature, invisible? Think about it. All the tools physicists had developed to detect particles relied on the fact that those particles had an electric charge. J.J. Thomson had bent cathode rays with magnetic fields because they were charged. Rutherford had seen alpha particles bounce off nuclei because they were charged. A neutral particle would be a ghost. It wouldn't interact with electric or magnetic fields. It wouldn't leave a trail in a cloud chamber. It could fly through matter almost completely unseen. How do you hunt for a ghost? You have to look for the havoc it wreaks, the footprints it leaves in the snow, even if you can't see the creature itself. The hunt for the neutron became one of the great obsessions of physics in the 1920s. Many teams were on the prowl, using the increasingly sophisticated tools of nuclear physics. The breakthrough came from an unexpected direction. Other experimenters, like Irene Joliot-Curie, daughter of Marie Curie, and her husband Frédéric Joliot-Curie in Paris, were also on the trail. They were bombarding light elements like beryllium with alpha particles. They found that when they did this, the beryllium emitted a mysterious, incredibly penetrating radiation. This radiation could shoot through centimeters of lead. They thought it might be a form of ultra-high energy gamma rays, which are photons of light. It was a reasonable guess, since gamma rays are neutral and can be penetrating. But their interpretation didn't quite fit. When they placed a block of paraffin wax, which is full of hydrogen atoms, and therefore protons, in front of this mysterious radiation, they found that the wax itself then emitted protons that flew out with very high energy. They still thought the gamma rays from the beryllium were knocking the protons out of the wax. But the math was shaky. It was like suggesting a ping-pong ball, a photon of light, could collide with a bowling ball, a proton, and send the bowling ball flying. It's possible, but it would require the ping-pong ball to be moving at an impossibly, ludicrously high speed. This is where our hero of this chapter enters the story. A quiet, meticulous, and exceptionally thorough English physicist named James Chadwick. Chadwick had been a student of Rutherford's and was now his right-hand man at the Cavendish Laboratory. He had actually been looking for the neutron for over a decade. When he heard about the Joliot's results, he was immediately skeptical of the gamma-ray explanation. He had a hunch that this mysterious penetrating radiation was not gamma rays, but the very thing he'd been searching for, the neutron. In a feverish burst of activity over a few weeks in 1932, Chadwick performed a series of brilliantly simple and conclusive experiments. He repeated the Joliot's work, but added crucial twists. He bombarded beryllium with alpha particles to produce the mysterious radiation. But then, instead of just using paraffin wax, he targeted other materials too. He aimed the radiation at a gas and measured the energies of the atoms that were knocked flying. His logic was impeccable. If the mysterious radiation was made of gamma rays, photons, which have no mass, then the energy of the knocked out atoms should follow a certain pattern. But if it was made of particles with a mass roughly equal to a proton, like the hypothesized neutron, then the energy pattern would look completely different. It was a classic process of elimination. The results were unambiguous. The energies of the knocked out atoms were far, far too high to be explained by massless photons. The only thing that could possibly cause such powerful kicks was a particle that had mass, a real hefty bullet. By carefully measuring the energies of the knocked out protons from paraffin and other nuclei, Chadwick could calculate the mass of the incoming neutral particle. It came out to be almost exactly the same as the mass of a proton. The ghost had been weighed and measured. He announced his discovery in a paper modestly titled "The Existence of a Neutron." With that, the puzzle was solved. The neutron had been found. The nucleus was not just made of protons. It was a tight little club of protons and neutrons, collectively called nucleons. The proton defined the element, its atomic number, and the neutron provided the extra mass, contributing to the atomic weight. Now everything made perfect sense. A helium nucleus has 2 protons and 2 neutrons, giving it a mass of 4. Carbon has 6 protons and 6 neutrons, for a mass of 12. Oxygen has 8 protons and 8 neutrons, for a mass of 16. The periodic table finally made complete sense. Chadwick's discovery of the neutron was the final piece needed to complete the classical picture of the atom. It was a picture we all learn in school, a central nucleus of protons and neutrons, with electrons whizzing around in shells. It's a satisfying picture, a complete picture. But as we know by now, in physics, every answered question opens a dozen new ones. The discovery of the neutron didn't just complete the atom, it opened the door to the world of nuclear physics. Now scientists could understand isotopes, atoms of the same element, same number of protons, but with different numbers of neutrons, giving them different weights. It explained radioactivity more clearly, and tragically, it soon showed the path to nuclear fission and the immense power for both creation and destruction locked within the atomic nucleus. But for that one moment in 1932, it was a pure triumph of science. James Chadwick, the careful, persistent hunter, had finally captured the ghost. He had found the neutral piece of the puzzle, and in doing so, he gave us the last key to understanding the building blocks of our ordinary world. It seemed like the end of the road, but ahead lay a path leading somewhere even stranger, into a hidden world of particles that were anything but ordinary, a world that would become known as the particle zoo. With the discovery of the neutron, it seemed like the atomic puzzle was complete. The building blocks of all matter were in place: electrons, protons, and neutrons. But the universe, as it turns out, is far more inventive and weirder than that. The same tools used to discover these particles, namely smashing things into each other at high speeds, were about to open up a Pandora's box of new, even stranger particles. This new era of discovery was driven by the invention of more and more powerful particle accelerators, or atom smashers. Instead of relying on natural radioactivity to provide projectiles, scientists could now create their own beams of particles, accelerate them to tremendous speeds, and slam them into targets with enormous energy. When you do that, you don't just break things apart. You can actually create new matter from pure energy. Thanks to Einstein's famous equation, E equals mc squared. It's like smashing 2 grand pianos together at high speed, and not just getting broken pieces of wood and wire, but also producing flutes, violins, and trumpets from the energy of the collision. It was in the debris of these high-energy collisions that a whole new world began to appear. The first of these new particles was found not in an accelerator, but in a natural source, cosmic rays. These are high-energy particles from outer space that constantly bombard Earth's atmosphere. In 1936, while studying cosmic ray interactions in a cloud chamber, a device that makes particle tracks visible, American physicists Carl Anderson and Seth Nettermeyer saw something baffling. They saw a track of a particle that curved in a magnetic field, just like an electron, but it curved the wrong way. It had to be positively charged, and it was much heavier than an electron. It didn't lose energy as quickly as an electron would. They had discovered a new particle, identical to the electron in every way, except it had a positive charge. They called it the positron, the first known example of antimatter, the story of which we have described in our antimatter video. Go and check it out if you want to, how antimatter was discovered. The positron is the anti-electron, but it had been predicted. Just a few years earlier, a brilliant British physicist named Paul Dirac had developed a new equation to describe the electron. His equation had two sets of solutions, one for the familiar negative electron and one for a positive electron. At first, he thought it was a mathematical quirk, but Anderson's discovery proved it was real. For every particle, there is a corresponding antiparticle, a mirror image with opposite charge. The universe has a wonderful sense of humor and a deep love for surprises, and its favorite delivery method for these surprises was, and still is, cosmic rays. Now let's talk about cosmic rays for a second, because they're amazing. They are not actually rays of light. The name is a bit of a misnomer. They are mostly superfast, high-energy atomic nuclei, protons mainly, that are blasted across the universe by exploding stars, black holes, and other cosmic catastrophes. They are nature's own particle accelerator, and they are constantly raining down on Earth from deep space. When these cosmic bullets smash into the atoms in our upper atmosphere, they create spectacular showers of secondary particles, a shrapnel of subatomic debris that falls toward the ground. For physicists in the first half of the 20th century, before we could build powerful accelerators, studying this cosmic shrapnel was the best way to find new and exotic particles. It was like lying in a field after a fireworks show, looking for interesting new pieces of fallen star stuffs. In 1937, Carl Anderson and Seth Nettermeyer were again busy with their cloud chamber. With the discovery of anti-electron under their belt, they once again saw a track that made them scratch their heads. It was a particle, that was clear. It had a charge, because it curved in the chamber's magnetic field. But it curved differently. From how it curved, they could tell two things. First, it was heavier than an electron, a lot heavier, about 207 times heavier in fact. But second, it was much, much lighter than a proton, which is nearly 2,000 times heavier than an electron. It was sitting in this awkward middleweight class all by itself. It was like finding an animal footprint that was too big to be a dog's, but too small to be a bear's. What was this thing? They named it the mesotron, later shortened to muon, and for a long time it was called the mu meson. But we'll get to why that changed. And its discovery was met with utter bewilderment. It wasn't just a new particle. It was a new particle that seemingly had no reason to exist. It was a complete copy of the electron in almost every way. It had the same negative charge. It felt the same electromagnetic force. It didn't feel the strong nuclear force. But it was fat. It was a heavy electron. And it was unstable. Where a regular electron is stable and lives forever, A muon lives for just over 2/millionths of a second before it spontaneously decays into an electron and a couple of neutrinos. This is where we get one of the most famous and relatable quotes in all of physics. The brilliant physicist Isidore Isaac Rabi, upon hearing about the discovery of this pointless middleweight particle, simply exclaimed, "Who ordered that?" It wasn't said in anger, but in genuine, amused astonishment. It was the perfect expression of how everyone felt. The menu of the universe seemed to be set. Protons, neutrons, electrons. That was the meal. It was satisfying and complete. And then the universe's kitchen had just sent out this weird, heavy, unstable thing that nobody had asked for, and that didn't seem to go with anything else. The muon, from the day it was discovered, was a particle without a purpose. It played no role in building atoms. It didn't hold nuclei together. It wasn't a carrier of a fundamental force. It was just there. A cosmic afterthought, an existential hiccup. But its importance was immense. The muon was a gigantic flashing sign from the universe. It was the first clear, undeniable proof that the particles they knew about, the ones that built stars and planets and people, were not the whole story. There was a whole other layer of reality, a whole hidden world of particles that had nothing to do with the architecture of stable matter. They were transitory, heavy, strange particles that lived fast and died young, existing only in high-energy collisions before decaying back into the familiar stuff. The muon was the first resident of what would soon become an entire particle zoo, a menagerie of strange and wonderful creatures that would eventually force physicists to dream up the quark model to make sense of it all. It was the first hint that the universe was far, far weirder and more wonderful than anyone had dared to dream. The puzzle wasn't almost complete. They had just found the corner piece, and now they realized the box contained a picture they couldn't even imagine. The next big discovery came in 1947, again from cosmic rays. A team led by Cecil Powell at the University of Bristol in England used photographic emulsions to track particles. They found a particle that was heavier than the muon, but lighter than the proton. It was called the pion, or p-meson. This was a hugely important discovery because it turned out to be the particle that Hideki Yukawa had predicted back in 1935. Yukawa had proposed a theory for the strong nuclear force, the incredibly powerful glue that holds the atomic nucleus together, against the tremendous repulsive force of the positively charged protons, crammed into such a tiny space. He said this force must be carried by a particle, just as the electromagnetic force is carried by the photon. He calculated that this particle should have a mass about 200 times that of the electron. The pion fit the bill perfectly. It was the carrier of the strong force. A proton and a neutron could exchange a pion, and in doing so, they would be held together. The discovery of the pion was a triumph for theoretical physics. As accelerators got more powerful in the 1950s and 1960s, the floodgates opened. Dozens and then hundreds of new hadrons, particles made of quarks, though we didn't know that yet, were discovered. There were kaons, lambdas, sigmas, xes, deltas. It was a true particle zoo. They were classified by their mass, their charge, and a new property called strangeness, which described how they were produced quickly in collisions but decayed slowly. This zoo was chaotic and confusing. There had to be an underlying order. The order was found. In 1964, two physicists, Murray Gell-Mann and George Zweig, independently proposed a radical solution. What if all these hadrons, the protons, neutrons, pions, kaons, and all the rest, weren't fundamental particles at all? What if they were made of even smaller, more fundamental building blocks? Gell-Mann called them quarks, a nonsense word from James Joyce's Finnegan's Wake. Zweig called them aces. The name quark stuck. The quark model was beautiful in its simplicity. It proposed that all hadrons are made of different combinations of just three types, or flavors, of quarks: the up quark, the down quark, and the strange quark. The proton, for instance, is made of two up quarks and one down quark. The neutron is made of two down quarks and one up quark. The positive pion is an up quark and an anti-down quark. The strange particles like the kaon and lambda contained the strange quark. The charges worked out perfectly. The up quark has a charge of +2, 3, and the down and strange quarks have a charge of -1 by 3. This is why the proton 2 by 3 plus 2 by 3 minus 1 by 3 has a charge of +1, and the neutron 2 by 3 minus 1 by 3 minus 1 by 3 has a charge of 0. It was a masterpiece of theoretical organization. It brought order to the particle zoo. But were quarks real, or just a convenient mathematical trick? The smoking gun came from a series of experiments at the Stanford Linear Accelerator Center, SLAC, between 1967 and 1973. In deep inelastic scattering experiments, they did what Rutherford had done, but on a much smaller scale. They fired high-energy electrons at protons. Just as Rutherford's alpha particles occasionally bounced straight back off the tiny nucleus, the SLAC electrons occasionally bounced off incredibly hard, point-like specks inside the proton. These point-like particles had the exact fractional charges predicted by the quark model. Quarks were real. The proton and neutron were not fundamental. They were made of quarks. So we've reached the 1970s. The particle zoo is bustling. The quark model, proposed by Gell-Mann and Zweig, has brought a semblance of order to the chaos. It's explained that all those heavy, unstable hadrons, the protons, neutrons, pions, kaons, and the rest, aren't fundamental at all. They're just different combinations of three simple fundamental building blocks: the up quark, the down quark, and the strange quark. The proton is two ups and a down. The neutron is two downs and an up. A kaon has a strange quark in it. It's a beautifully simple system. Three quarks to rule them all. The universe, it seems, could be built on a tidy little trio. But if you were a theoretical physicist living inside this new theory, you might have started to feel a slight unease, a tiny, nagging worry. Because the same mathematical framework that so elegantly demanded the existence of quarks was also starting to whisper about a problem. A problem so serious it threatened to unravel the whole beautiful tapestry they were weaving. It had to do with a certain type of particle decay that wasn't happening. Let's set the stage. We have the weak nuclear force. This is the force responsible for certain kinds of radioactive decay. It's the force that allows a neutron to turn into a proton inside a nucleus, spitting out an electron and an antineutrino in the process. This is beta decay. Now, the weak force, as the name suggests, is very weak and only works at incredibly short ranges. But it also has another quirky property. It doesn't play by the same rules as the other forces. It has a handedness. It treats left-handed particles and right-handed particles differently. It's biased. It's a force with a preference. This bias, this violation of symmetry, was already a known and accepted weirdness of the weak force. But the theories that were being developed to describe it, theories that aimed to unify the weak force with the electromagnetic force into a single electroweak force, were incredibly precise and powerful. And they made very specific predictions about how often certain rare particle decays should occur. One of these predictions involved the decay of a strange particle called the kaon. Kaons are mesons that contain a strange quark. The theory predicted that a neutral kaon should very, very rarely decay into a pair of muons. This would be a process mediated by the weak force, and it would be what's called a flavor-changing neutral current. That's a fancy way of saying a particle would change its quark flavor from strange to not strange without its electric charge changing in the process. It's a specific, delicate, and very rare kind of decay. Physicists built incredibly sensitive experiments to look for this exact decay. They watched and watched, and they found nothing. The decay wasn't just rare, it was absent. It wasn't happening at all. The rate was 1 billion times smaller than the theories predicted. It was as if the universe had a law against it. This was a 5-alarm fire for theoretical physics. The beautiful, elegant electroweak theory, which was explaining so much else so perfectly, was predicting something that blatantly did not happen in the real world. It was a crisis. Either the theory was fundamentally wrong, or there was something huge missing from the picture. In 1970, 3 brilliant theorists, Sheldon Glashow, John Iliopoulos, and Luciano Maiani, stepped in with a daring and elegant solution. Their proposal is now known by their initials as the GIM mechanism, Glashow, Iliopoulos, Maiani. They looked at the problem and said, what if the reason this decay isn't happening is because it's being canceled out? Imagine you have 2 speakers playing the exact same sound. If you wire one of them backwards, it will produce a sound wave that is the exact opposite, the inverse, of the first speaker's wave. When these 2 opposite sound waves meet, they cancel each other out, and you get silence. This is called destructive interference. Jim proposed that something similar was happening in the subatomic world. The predicted decay was like one sound wave. But what if there was a second, hidden process? A second, opposite sound wave that was exactly canceling it out, resulting in the silence that the experiments were detecting. For this perfect cancellation to work, they calculated, there had to be a 4th quark. A new quark that was a partner to the strange quark, just as the up quark is a partner to the down quark. They called this proposed new quark the charm quark. The charm quark would have a charge of +3, just like the up quark, but it would be much heavier. Its existence would provide that second canceling pathway. The disastrous decay wouldn't happen because the 2 possible quantum paths for it to occur would destructively interfere, leaving nothing. The absence of evidence became the evidence for a new existence. It was a breathtaking piece of theoretical physics. They had looked into a void, a place where nothing was happening, and deduced the existence of a whole new fundamental particle. Of course, a theoretical prediction, no matter how elegant, is just a nice story until experiment proves it right. The hunt for the charm quark was on. It became the holy grail of particle physics. The race was intense, primarily between 2 major labs and 2 brilliant, fiercely competitive team leaders. On the west coast of the United States, at the Stanford Linear Accelerator Center, SLAC, was Burton Richter and his team. They were using a revolutionary new kind of machine called a collider. Instead of smashing a beam of particles into a stationary target, as earlier accelerators did, they designed a machine that accelerated 2 beams of particles, electrons and positrons, in opposite directions around a massive ring, and then smashed them together head-on. This is far more efficient because all the energy of the collision goes into creating new particles, like two cars crashing head-on versus a car hitting a brick wall. Richter's machine was called SPEAR. On the East Coast, at Brookhaven National Laboratory, was Samuel Ting and his team. They were using a more traditional, but still incredibly powerful, approach. They took a beam of protons and slammed it into a stationary beryllium target. Their strength was not in the collision energy itself, but in the magnificent precision of their giant detector. It was a complex marvel of magnets and sensors, designed to measure the products of these violent collisions with exquisite accuracy. Both teams were unknowingly circling the same prey. In the fall of 1974, the tension was palpable. At SLAC, Richter's team began seeing a huge, shocking spike in the production of certain particles at a very specific collision energy. It was a massive, narrow resonance, a sure sign of a new, unexpected particle. It was so unexpected and so dramatic that they thought their machine was broken. They spent days frantically checking and rechecking their equipment. The signal was real. They called this new particle the PSI particle, plus. At almost the exact same time on the other side of the continent, Ting's team at Brookhaven was also seeing something extraordinary. They were detecting a startling number of electron-positron pairs that were being produced with a very specific combined energy. This, too, was the signature of a new particle decaying in a specific way. They called their discovery the J particle, a symbol that resembled the Chinese character for Ting's name. The two teams were on a collision course with history. The rumor mill in the small world of particle physics went into overdrive. Each team heard whispers that the other had found something big. The race to publish, to claim the discovery, was intense. In a moment of high drama, the two teams independently called the same editor at the same prestigious journal, Physical Review Letters, to rush their papers into publication. The climax came on November 11th, 1974. Both groups were scheduled to give seminars at their respective labs to announce their findings. The news traveled fast. Richter at SLAC received a telegram from Brookhaven just before his talk, informing him of Ting's results. The energies matched, the properties matched. They had both found the same particle, a particle that was immediately and universally recognized as the harbinger of the charm quark. This simultaneous independent discovery sent a shockwave through the physics community so profound that it is remembered as the November Revolution. The particle itself is now known as the J-psi particle, a diplomatic hyphenation of its two names. What was it? The J-psi wasn't the charm quark itself, but a meson made of a charm quark bound to its own antiparticle, an anti-charm quark. This is called a charmonium state. Its incredible stability and sharp resonance were due to the fact that it was a perfect balance of opposites. This discovery was the slam-dunk evidence for the charm quark. The Jim mechanism was right. The missing piece had been found. The impact was immediate and profound. The discovery of charm was a triple victory. First, it saved the electroweak theory from its fatal flaw, providing the crucial canceling mechanism that explained the absence of the forbidden decays. Second, it provided gigantic support for the developing theory of the strong force, quantum chromodynamics, QCD, which described how quarks were held together by gluons. The properties of the J-psi meson matched the predictions of QCD perfectly. And third, it completed the second generation of matter. Now there were two pairs of quarks, the light ones, up and down, that build our everyday world, and the heavier ones, charm and strange, that are created in high-energy processes. The universe, it turned out, loved symmetry so much it had built itself in duplicate. The November Revolution didn't just add a new particle, it validated the entire, breathtaking theoretical framework of the Standard Model. It was a moment of stunning confirmation, a day when the universe winked and said, "You're on the right track." The fifth and sixth quarks were hunted down and found in the following years. The bottom quark, or beauty quark, was discovered in 1977 by a team at Fermilab led by Leon Lederman. They found a new particle, the upsilon, which was a bound state of a bottom quark and its antiparticle. The existence of the bottom quark strongly implied there had to be a sixth and final quark to complete the set, to pair with the bottom quark and allow the Standard Model theory to work correctly. This was the top quark, or truth quark. It was the hardest to find because it is incredibly heavy, over 170 times the mass of a proton. It took nearly 2 decades of work and the most powerful particle collider ever built, the Tevatron at Fermilab, to finally produce and detect the top quark in 1995. With that, the quark family was complete. Up, down, charm, strange, top, bottom. All the matter that makes up our everyday world is made of just the first two, the up and down quarks. The others are unstable and only created in high-energy collisions, but they are fundamental to the laws of the universe. While the quark story was unfolding, the story of the forces that govern them was also being written. We've mentioned the photon, the particle of light, and the carrier of the electromagnetic force. It was Einstein who, in 1905, proposed that light could be thought of as particles, later named photons, to explain the photoelectric effect. But the concept was fully developed within quantum field theory. The photon is a massless, chargeless boson, a force-carrying particle. It is the mediator of the electromagnetic force. When two electrons repel each other, they are actually exchanging a virtual photon. What about the other forces? The strong force, which holds quarks together inside protons and neutrons, also has a carrier particle. These are called gluons. Remember, quarks have a property called color charge. This is where quantum chromodynamics gets its name. It has nothing to do with real color. It's just a label for a quantum property. Gluons are the particles that carry the strong force between quarks. They are like the sticky glue that holds the quarks together, hence the name. Gluons themselves carry color charge, which means they can interact with each other, making the strong force very different from the electromagnetic force. Gluons were first observed indirectly in the late 1970s in the same electron-proton scattering experiments that confirmed quarks, and their properties have been measured with great precision since. Then there is the weak nuclear force, responsible for radioactive beta decay, where a neutron turns into a proton inside a nucleus. The theory for this force, developed by Sheldon Glashow, Abdus Salam, and Steven Weinberg, predicted that it should be carried by 3 very massive particles, the W positive, the W negative, and the Z0 bosons. Their large mass is why the weak force is so short-ranged and weak. Discovering these particles was a monumental task. It required building a collider powerful enough to actually create them. That machine was the Superproton Synchrotron, SPS, at CERN. In a legendary series of experiments in 1983, led by Carlo Rubbia and Simon van der Meer, the W and Z bosons were discovered. It was a spectacular confirmation of the electroweak unification theory, and it earned Rubbia and van der Meer the Nobel Prize just a year later, one of the fastest recognitions in the prize's history. And we cannot forget the neutrino. This ghostly particle was first proposed by Wolfgang Pauli in 1930 out of desperation. He was studying beta decay and saw that energy and momentum seemed to be disappearing, violating fundamental conservation laws. To save these laws, he proposed an impossible particle, one with no charge and little to no mass that could carry away the missing energy without being detected. "I have done a terrible thing," he said. "I have postulated a particle that cannot be detected." Enrico Fermi later named it the neutrino, Italian for little neutral one. It took 26 years to finally detect one. In 1956, Clyde Cowan and Frederick Rhines set up an incredibly sensitive experiment next to a powerful nuclear reactor, which they knew would be producing a flood of antineutrinos. They finally caught them through a rare interaction with protons. The neutrino was real. We now know there are 3 types, or flavors, of neutrino, each associated with a charged lepton. The electron neutrino, the muon neutrino, discovered in 1962, and the tau neutrino, indirectly inferred for decades and finally directly observed in 2000 at Fermilab. Neutrinos are the most elusive of particles, able to pass through light years of lead without interacting, yet they are the second most abundant particle in the universe, after photons. This brings us to the last piece of the puzzle, the one that gives mass to all these other particles. In the 1960s, the developing Standard Model had a problem. The theory demanded that force-carrying particles like the W and Z be massless, like the photon, but we knew they were very heavy. The solution was a mechanism proposed by Peter Higgs, François Englert, Robert Brout, and others. They suggested that the entire universe is filled with an invisible field, now called the Higgs field. As particles move through this field, they interact with it. Some particles, like photons and gluons, don't interact at all and remain massless. Others, like the W and Z bosons and quarks and electrons, do interact, and this interaction is what we experience as their mass. The excitation of the Higgs field would manifest as a particle, the Higgs boson. Finding this particle became the holy grail of particle physics. It took nearly 50 years and the largest, most complex machine ever built by humankind, the Large Hadron Collider, LHC, at CERN. On July 4, 2012, the world watched as the 2 major LHC experiments, ATLAS and CMS, announced the discovery of a new particle with the expected properties. It was the Higgs boson. The final cornerstone of the Standard Model was in place. And so, our treasure hunt, our grand journey into the heart of matter, reaches its conclusion, for now. From a curious green glow in a cathode ray tube to the monumental collision chambers of the LHC, we have peeled back the layers of reality one by one. We discovered the electron, the proton, and the neutron, and thought we were done. Then we found that the nucleus itself was a universe of complexity, giving us pions and the weak force bosons. We found a mirror world of antimatter with the positron. We found unnecessary yet fundamental particles like the muon and the ghostly neutrinos. We discovered that the protons and neutrons themselves are made of even smaller, fractionally charged quarks held together by gluons. And finally, we found the key to mass itself, the Higgs boson, the manifestation of the field that gives shape to our universe. This is the Standard Model of particle physics, a family of 6 quarks, 6 leptons, the electron, muon, tau, and their 3 neutrinos, and their antiparticles, all governed by the 4 fundamental forces carried by the photon, the W and Z bosons, and the gluons, all set upon the stage of the Higgs field. It is the most successful and precise scientific theory in human history, capable of predicting the outcome of experiments to astonishing accuracy. It is the story of how we discovered what we are made of. It is a story of human curiosity, perseverance, and genius. It is a story that tells us that the universe, at its very heart, is built on rules that are beautiful, mathematical, and utterly strange. And the most amazing part? The hunt isn't over. Dark matter, dark energy, the mystery of gravity's place in the quantum world. They tell us that the map is not yet complete. The treasure chest of the cosmos still has secrets waiting to be found. But that is a story for another day. Good night, and have deep sleep.